All right, so after a lengthy calculation, we have determined a formula for the quotient rule. Now, when I'm using this on a day-to-day basis for calculating derivatives of functions, it is very important to keep track of what happens to the numerator and what happens to the denominator. Different things happen to these functions under the quotient rule. So, reading it literally, I see I've got denominator times the derivative of the numerator minus numerator times the derivative of the denominator. And the new denominator here is the square of the old denominator. Well, that's a bit wordy to memorize. So there's a cute little rhyme I like to use to remember this stuff. The original function is a fraction with a numerator and a denominator. Rather than call them f and g, let's say that that function on top has the name high, and the function on the bottom has the name ho. A little unconventional, but sure, we can call our functions those things. Then the derivative of high on ho is this. Take ho-d high minus high-d ho, square the bottom, and away you go. So the trick is that I know my numerator has to be the function high of x because it's on top, it's high. And I know that I've remembered the formula correctly because my little rhyme there actually rhymes. So if I was going to say, it's like, oh, is that ho of x d high minus high d ho square the bottom of o? Ah, yes, that rhymes. So that's the correct formulation. If I did high d ho minus ho d high square the bottom and away I go. No, that's not it. That's not it. Just a nice little check. Something that works for me. Let's actually use this formula now. Here I have a rational function. Y equals x squared plus x minus 2, all on x cubed plus 6. So my two different functions here, my numerator and my denominator, my f of x and my g of x, my high and my ho, these are both polynomials. High is the function x squared plus x minus 2. Ho is the function x cubed plus 6. I can do both of these derivatives because they're both polynomials. The quotient rule tells me that y prime will be equal to ho d high minus high d ho, square the bottom and away I go. So I've got the original denominator, x cubed plus 6, times the derivative of the original numerator, derivative of x squared plus x minus 2. From that, I must subtract the original numerator, x squared plus x minus 2, times the derivative of the denominator, derivative of x cubed plus 6, and the new denominator will be the quantity x cubed plus 6 squared. Okay, so I can calculate those derivatives, the ones in my numerator here. The derivative of x squared plus x minus 2 is 2x plus 1. I can do every single piece using the power rule, and I just add them up the same as they were in the original polynomial. The derivative of x cubed plus 6 is going to be 3x squared for the same reason. Derivative of x cubed is 3x squared. The derivative of 6 is 0. So the derivative of quantity x cubed plus 6 is the derivative of x cubed plus the derivative of 6. And I just get 3x squared. Okay. Now, I do have a little bit of multiplication to work out, but at this point, the multiplication step takes some time, but it's not something that I would call mentally taxing. It's just tedious, not necessarily difficult. I can go ahead and multiply all these things out. I get the difference of two different polynomials divided by quantity x cubed plus 6. So I can combine all the identical powers of x, and I find that this derivative is equal to quantity negative x to the fourth minus 2x cubed plus 6x squared plus 12x plus 6, all divided by quantity x cubed plus 6 squared. Now, for these kinds of problems, I usually end up with my original denominator squared because that's what it says in the quotient rule formula. I'm not going to bother to multiply that out any further. Goodness, haven't I done enough algebra for one problem? It's my official opinion as your professor to say, yes, we have done enough.